Okay. Good morning or good afternoon to everyone present here. My name is Haritha, and I'm here with my co-author today, Sahana, and our paper is on cryptocurrency price prediction using sentiment analysis of tweets. We are both from PES University, India, from the Electronics and Communications Engineering Department. This is just how we're going to go through the paper today, starting with just something about the abstract, what exactly we're trying to solve, our intention behind taking up this research project, and related works that we studied before we built our own methods, and a little bit in detail about the methods that we've used. A more in-depth discussion of the results and a summary summarizing everything that we're going to see now. So just the abstract, Twitter is becoming a very popular platform. Twitter is becoming an extremely popular platform for opinion exchange and discussion on traditional financial markets, as well as any kind of asset market discussion, asset class discussion, and cryptocurrency is no exception. Twitter has a lot of communities that discuss cryptocurrency, and these communities hold a lot of influential investors within the cryptocurrency market. So our paper studies these tweets and tries to predict the sentiment of these tweets and sees if using the sentiment of these tweets, the price prediction of Bitcoin can be enhanced. And for the sentiment prediction, we use a BERT-based model, and for the price prediction, we use a gated recurrent unit. So in this study, we have our results for the sentiment prediction was the metric we use is the mean absolute percentage error. For the sentiment prediction, we have a 9.45% error, and for the final price prediction, we include the historical price in that, we have 3.6% error. So motivation and problem statement. So the motivation and problem statement of this research project is that we see that there is a lot of link between traditional financial markets, cryptocurrency markets. They are all the cryptocurrency markets are influenced by S&P 500 as well as the general market sentiment, and there are we had done quite a lot of literature survey based on for this particular aspect to see what are the things that affect the cryptocurrency market aside from the general economic health of big economies. We also had just general market sentiment that was either expressed through organized media like news or unorganized media like Twitter. So Twitter is more discussion oriented, and there is a lot of sentiment and kind of discussion on these platforms. So media expression through this Twitter is something that has been studied for traditional markets, but we wanted to collate it for cryptocurrency and see what can be done to enhance price prediction in this aspect. The class that we're talking about, the asset class, which is Bitcoin, is one of the most volatile asset classes to exist. And it has had a high volatility for a while, since its inception itself. And anything that can enhance our understanding of this asset class would help us understand the nuances and how these markets behave. So our project aims to study if there is a correlation or an enhancement in our understanding of these prices and the behavior of the cryptocurrency market through market sentiment expression, specifically through Twitter as a social media platform. So over to Sahana to talk about the related work that we studied before we based our project on our methods.
Okay, so let's move on to the related work in this field. I will briefly be talking about the price prediction methods of crypto and the sentiment analysis that were previously implemented. So starting off with sentiment prediction, it can be ideally done via two methods, either rule-based or machine learning methods. When we talk about rule-based, weighted, which is balance, aware dictionary, and sentiment reasoner is the first thing that comes up. It's a rule-based sentiment analysis tool that is specifically designed for analyzing sentiment in social media content. So this works by analyzing text and assigning a polarity score to it, indicating whether the sentiment of the text is positive, negative, or neutral. It also assigns intensity scores to each of these polarities, indicating the degree of emotion expressed in the text. One of the advantages of Vader is that it's specifically trained on social media text, which can be quite different from other types of text, such as formal written documents. Whereas it takes a backseat when it comes to text that's highly context dependent. And a few more disadvantages are that it has limited language support and lacks customization. So this is where BERT comes into play. We'll be talking more about BERT when we explain our methodologies. Now, moving on to the machine learning methods in sentiment prediction itself. One of the research papers predicted sentiment for a common data set against different ML methods to compare its accuracy. A few of them include naive-Bayes, which gave an accuracy of 79%, SVM an accuracy of 84%, decision tree 75.16%, and CNN an accuracy of 74%. So as evident from the results, SVM performed better than the others. So now let's move on to price prediction. I'm going to talk about the ML methods that were used to predict prices of highly volatile cryptocurrencies. So machine learning techniques such as regression, neural networks, and decision trees can be used to build predictive models that can forecast the future price of highly volatile currencies based on historical data and a few other factors. So previously, price prediction was implemented using Bayesian regression, which gave a turnover of twice the amount invested in the last 60 days. Another scenario in the paper talks about deep reinforcement learning that enabled a 10-time increase in the value of the portfolio. But when it comes to predicting time series data, LSTM and GRU have an upper hand. Both these variants of recurrent neural networks can store previous data, hence making it very useful when it comes to regression problems with respect to time series. Again, we'll be deep diving into their architecture in the next few slides while presenting our methodologies. Let's move on to combined methodology, which is relevant to us. So let's go to a few papers that discuss both sentiment analysis and price prediction together. Now, sentiment analysis here involves analyzing social media and news sentiment to predict market sentiment and the potential price movements. This method uses natural language processing techniques to analyze the tone and content of social media and news articles to identify where the potential trading signals are. Now, a research paper mentions an instance like this, where the data set includes tweets pertaining to a particular type of cryptocurrency. The sentiment analysis model, which was run against this data set, and each tweet was labeled as positive and negative. And when price prediction was done against this, taking sentiment into account as an additional factor, an accuracy of 77% was drawn. Hence concluding that there is a correlation between the sentiment of the market and the prices of cryptocurrencies, thus strengthening the relevance of our paper over here. Now over to Haritha to continue.
Okay, sure. So the reason we have added a few slides about our data set is because the data set inherently formed a strong point in our model. So our data set consists of two sources. One is the Twitter data and the other is the historical price data. So the Twitter data is sourced from Kaggle, and it's from a data set that scrapes daily tweets about cryptocurrency. So it finds tweets either based on searching for the word directly or for hashtags. So this is unprocessed data sets. It includes spam tweets, giveaway tweets, all of these irrelevant tweets as well. And shortly, I will get to how we handle that. But this Twitter data set only has the number of followers. Like on the table, as we can see on table 1, the second column, this cryptocurrency tweets column, these were the features present in the Kaggle data set. As you can see, there is no sentiment feature itself, and I will get to how we handle that, because finding manually labeled Twitter data for large data sets is not yet as satisfactory as we had hoped it to be. For historical price data, we source that from Yahoo Finance, and it consists of in-depth price data, high, low, close, open, adjusted close, which is the close price adjusted against the dividends paid that day, and the trade volume of that day. So as we can see on table 1, there are a lot of features from both the data sets, and we felt that it would be apt if we included ones that have high correlation with the output and not just um, less relevance. So for the cryptocurrency tweets as well as the Bitcoin historical price data sets, we had ran correlation analyses and identified that there are 4 from the historical price data as well as and 5 from the cryptocurrency tweets data. And these 11 features, along with the sentiment that I'm going to talk about in the next slide, became our data set for the price prediction. So, of course, when talking about, you can think about our project as 2 parts. First is the sentiment prediction, and the second is the price prediction. Talking about the sentiment prediction, we only used cryptocurrency tweets, just the text field. Nothing else was relevant there. So for the first part of our project, we only used this one particular field itself, and we added the sentiment to this to this data set. And along with the existing 5 features, added a 6th feature called sentiment, and used these 4 features from the price data set and made 12 features for the final price prediction data set for the second half of the project. So the Twitter data set, as I had just mentioned, does not contain any sentiment variable. So we used Vader, the method that Sahana had mentioned under relevant work, to add sentiment to our data set. So the thing about Vader as a methodology to add sentiment is that it has an F1 score of 0.96 and is reported to outperform human raters. And there is an in-depth paragraph about this in our paper. And Vader takes into account not only negations and contractions, but also superlatives. So if I say, as I've mentioned here, like good and good with 3 exclamation marks are added as separate, have separate sentiment scores. So good is more, good with the exclamation marks is more polar. So it takes all of these into consideration, especially because it's a very social media oriented manual labeling platform. So the question itself can be, if it has an F1 score of 0.96 and it's reported to outperform human raters, why did we use this to make our data set and not just do the project with it itself? The thing about that is that for finance related tweets, or specifically with respect to markets, we felt that through our experiments, we also saw that the context of the tweet or the context of the emotion was very important, because Vader is a rule-based method. It takes individual words, maps it against a dictionary, and calculates a score. It does not have contextual embeddings. There are multiple line tweets and threads and all of these multiple ways of sharing data on Twitter, and in such a way that context becomes extremely important. So when we do not have contextual data or contextual embeddings rather, because the Vader does not have the embedding itself, it's just a rule-based sentiment, it becomes the most important tweets become mislabeled, right? So that we felt that the context became inherently very important. Also, a more important reason was that it's rule-based, and our just our tweet data set is about 1.2 million tweets, and the the time frame that we use for these data set, for the Twitter data set, we had used for training 1 year worth of data, and we tested on 1 month for the entire price prediction model. So just for the 1 year itself, we had scraped 1.2 million tweets, and it was a large number to do by a rule-based. It wasn't scalable at all. So we did it once and used it as the feature to train on. So table 2 Another thing is that Vader gives continuous scores. So it isn't a sentiment classification problem, it's a sentiment prediction problem now, because it can, because as we had mentioned, there are superlatives and there are different versions of just good, for example, and all of that. So table 2 represents our split between training, testing, validation, remove, and total. So talking about the removed tweets, so the thing is that there are a lot of spam tweets in this particular data set. So what we did was that in the data pre-processing, tweets with irrelevant hashtags like giveaway were removed. Tweets with users from users with less than 10 followers were also removed. Tweets with zero text and only hashtags were also removed. So after all this, around 200,000 tweets were removed as being classified as spam. It isn't necessary that every account under 10 followers is spam, but just for the sake of finding truly meaningful data and measuring influence on a social media platform as the number of followers, we just felt that it was safe and a reasonable decision to make at the time. So one thing that I would like to highlight is that this was the dataset distribution before augmentation, and this was the dataset distribution after augmentation. Why was this dataset augmentation even required? The thing is that our dataset had a significant degree of imbalance according to the results of our internal statistical analyses. About 32% of the data set was strictly neutral, even though Vader provides a continuous a continuous sentiment score. Around 32% of the data set was strictly zero. The 25th percentile and the 50th percentile of the data were also strictly zero. So about out of 1.2 million tweets, 412,000 was strictly neutral, and more tweets were around this region itself. So to solve this, we did three particular operations in the data augmentation. We removed half of the strictly neutral tweets and therefore undersampled to avoid overfitting, because we did find a lot of overfitting in just the spam removed data set. Like with just removing spam, it wasn't enough. And we added Gaussian noise around the center to about a quarter of the data set. And it was the Gaussian noise had a mean of 0 and a standard deviation of 7% of the input signal. And this was decided through trial and error and the respective MAPE values that were obtained. And the graph for that is also in our paper. Third operation that we did perform was that spam tweets were being classified as neutral and adding to the class imbalance. So aside from the spam predefined criteria that we have for spam, we did one more filter that we removed tweets with only emojis. There were a lot of tweets that had only emojis, but a hashtag Bitcoin. So it would pick up as a tweet. So we removed that. And after that, you can see the results in terms of the distribution as well as the outcome of the augmentation. So this led to a more stable model, in that the model had different type of information to learn rather than overfitting very soon, because more than 80% of the initial data set was around 0 or strictly neutral. So this was this is just an overview of the method that we have been talking about, just to put a figure to it. The input tweet data goes to a BERT-based neural network, which performs sentiment analysis, and it gives out a continuous predicted sentiment score. Or a sentiment score that is continuous in nature. Then we append or add this to historical price of Bitcoin and we match it based on date. And this whole data set, which was the 12 features that we were earlier talking about, is passed to the GRU. And the GRU provides for the specific time period. So we have 1 year worth of training data, and the 1 year of training data ended 5th August 2022. So 5th July 2022. And from 5th July to 5th August, the output price is given. So a 3-step summary is that we collect the data streams collated in a single clean comprehensive data set. we pass the tweet data through the BERT-based sentiment analysis model, and using GRU to forecast the prices as well as using the prices as well as other sentiment features. So let's talk a little bit more in detail about the specific algorithms that we have used for this project, starting off with the BERT-based sentiment analysis. So the sentiment prediction in this paper is done using a fine-tuned FinBERT-based model. FinBERT is a language model based on BERT, built to tackle NLP problems in the financial domain. So on various NLP tasks, pre-trained generic language models have produced really good results. So one of the most effective language models now in use is BERT, and the transformer encoder is the foundation of this specific concept. So the makers of the BERT model have given two options. One is BERT-based and another one is BERT-large. There are some recommendations based on how to train the BERT model. And of course, these recommendations are meant for extremely huge data sets. Prediction or the BERT language model is what is used for very large scale internet-wide operations. So we used BERT-based in this study, and the authors recommend fine-tuning up to over 4 epochs of training, and there are 5 batch size recommendations. They also have provided 3 learning rate recommendations. Since comparatively, even though our data set is big, comparatively for other large scale operations, our data set is smaller. We were able to find that a learning rate of 5 epoch minus 5 and a batch size of 32 or trained over 2 epochs works best for us. And the maximum that the makers itself recommend is 4 epochs for really big data sets. So 2 epochs was perfect for us. And we analyzed this through YAML sweeps, and we were able to find the metric for us, and we were able to find that it works best like this. So this is just an overview of the BERT structure. And since the BERT design is not a sequence-to-sequence model, it ignores the decoder network and simply uses a transformer encoder. Even though it can be used in such tasks. So that was an overview of the BERT model that we used. Now Sahana will talk more about the GRU to forecast the Bitcoin prices.
The price of highly volatile cryptocurrencies using GRU, which is the gated recurrent units, a popular method in the field of deep learning. So GRU is a variant of recurrent neural network that is designed to overcome some of the limitations of traditional RNN, such as the vanishing gradient problem. Now, GRUs are able to selectively update and forget information, making them well suited for time series data such as cryptocurrency prices. Now, you might have a question as to why GRU and not LSTM when both can get over the vanishing gradient problem. But a few noteworthy observations that make GRU better than LSTM are that it has 2 gates, which is update gate and the reset gate. Can you move on to the next slide? Yeah, so the update gate retains information, the relevant information, and the reset gate discards the irrelevant information. So GRU has 2 gates, whereas LSTM has 3. So it has a few tensor operations, it takes in lesser parameters. So it's saving memory and also increases computation power meanwhile. So how do we use this for predicting price? By taking in sentiment as a feature. So the data set, as we mentioned before, we split it into independent and dependent samples. We scale it and reshape them to fit the model. We split it into training and testing data sets. Training includes 80% of the data set and testing is the 20%. Post this, we move forward to build our GRU model with the parameters over here include the number of units that we need. The activation layer, as seen in the structure, it's going to be tanh, and the recurrent activation layer from the structure again is going to be a sigmoid layer. Now, a dropout layer is added to prevent overfitting in this case. This is a penalizing for complex models. Now, a dense layer is added because this is a regression task. Once this model is fit and built, we go ahead to predict values of cryptocurrencies by testing it against our testing data, and we compare the actual and the predicted values to see how well our model has performed. Can we move on to the next slide? Okay, so now I'll be talking about the most important bridge, the result of our methods. Okay, so this table shows us the results of sentiment prediction against different algorithms for a standard data set that was collected over the time frame of 5th August to 5th September and 5th September to 5th October. So we can see from the results that FinBERT performs exceptionally well, giving an average mean absolute percentage error of 9.06 against the test data and 9.85% against real-time data. This is closely followed by GRU, which gives a mean absolute percentage error of 9.31% against test data and 11.52% against real-time data. BERT-STM, whereas takes a backseat here, it provides a result of 11.20% mean absolute percentage error against test and 12.17 against real time. Let's move on to GRU, price prediction results. Yes, thank you. Now this table shows us the results when GRU was used for predicting the price against the data set that was collected previously, and sentiment was predicted as well. So we are doing this to maintain a standard data set and predicting sentiment for the same data set, predicting the price for the sentiment that was generated previously. So this, while predicting price, we use sentiment as a feature and run the GRU model against it. This gives as an average mean absolute percentage error of 3.6% over both the time periods. Moving on to the next graph. This graph over here serves as an extrapolation of the previous one, basically providing an additional viewpoint to enhance the overall clarity of our analysis. It demonstrates the degree of overlap over here between the actual and predicted prices. The predicted price is what you see in blue, and the actual price is what you see in yellow. And this provides a clear visual representation of the MAPE value, which was previously mentioned. The graph is plotted against the time period as mentioned as well. So you can see that there's a clear difference. You can see the representation that's made of the MAPE value as well. It provides further support for the overall effectiveness of our model, and it also helps us to reinforce the validity of our conclusions of 3.6%. The next graph over here is the MAPE value for each prediction. So this graph provides a visualization of the changes in the MAPE value over the specified time frame. It shows that our model performs reasonably well and does not stick to the momentum. So the presence of outliers in the graph over this time period also serves as an evidence supporting this claim, demonstrating that our model is capable of capturing volatility as well. So you can see there are places where there are outliers when the graph goes really high, meaning it doesn't stay stable and captures volatility during that time period as well. Let's summarize whatever we've spoken in today's talk. So our paper is primarily focused on predicting the prices of cryptocurrencies based on the prevailing market sentiment, given that high correlation exists between both these factors. Now, to this end, we leverage FinBERT, which is a state-of-the-art language model, to predict market sentiment by analyzing tweet data. Our experiments show that this approach results in a mean absolute percentage error of 9.85%, which is superior to the performance of other popular models such as GRU and BERT-STM. Furthermore, we find that the GRU model outperforms all other machine learning based models as well for predicting the price of highly volatile currencies and achieving a mean absolute percentage error of 3.6%. So thus our results indicate that by incorporating sentiment analysis into our model, we're able to achieve greater accuracy in predicting cryptocurrency prices, particularly in the context of highly volatile markets. We are now open for Q&A. Thank you.